quantum engineering seminar, which is organized.
Recording in progress.
Oh, you want to record, so I'll start again then. Got it. All right. This is the first session of the Quantum Engineering Seminar, organized by Philip Hemmer and Alexei Sokolov, who are both based at Texas A&M. We have 4 20-minute invited talks and 1 15-minute contributed talk at the end. The first talk is to be given by Stefan Osterman from Harvard, and the title is Hardware Efficient Quantum Simulation of Strongly Correlated Molecules and Materials with Reconfigurable Atom Arrays. So please go ahead, share your screen.
Yeah, great, thank you. Just give me a second to share my screen. So can you see my slides now?
Yeah, very nice.
Great, and you should also see a laser pointer now. All right, perfect. So yeah, thank you so much, and thanks for the introduction. And yeah, my name is Stefan. I'm a postdoc at Harvard, and it's great to present like some recent results we got here at Harvard about hardware efficient quantum simulation of these strongly correlated molecules and materials with these Rydberg atom arrays, which are like really exploding at the moment in the physics community. And yeah, thanks for the organizers to actually allowing me to present this. And this is work done in collaboration with 3 groups. The first one is Martin Head-Gordon's computational quantum chemistry group at Berkeley, and Misha Lukin's group here at Harvard, as well as Susanna Jelin's group here at Harvard. And there was like a big group of people involved in this work, and it was a great fun project to collaborate and brainstorm and really trying to make quantum chemistry simulations happen on those reconfigurable Rydberg atom arrays. And let me just give it a try here real quick. Sorry, I see myself up here. Let's move that down here. Great. All right. So, according to many, and I think they're becoming more, we live in what people call the quantum decade, meaning that large companies, small companies, labs are trying to build useful quantum computers or quantum devices, which should have some impact on our lives and our society in the long run. And of course, now the question arises, what are we using these quantum devices for? And from the many things floating around, one can sort of compile a list of things like containing factoring, quantum machine learning, optimization problems. But one topic which is usually always part of this list is also quantum chemistry, or material science in a more general framing. And today's talk is exactly about this part of this list, quantum chemistry on quantum devices. And quantum chemistry in general is about solving an electronic structure problem for a certain configuration of electrons and nuclei, where in a Born-Oppenheimer approximation, one usually considers the kinetic energy of the electrons, and the electrons and the nuclei, they interact via Coulomb interaction. And then one has to solve sort of for the spectrum of this Hamiltonian, which in general is hard. It turns out, however, that advancing quantum chemistry with quantum devices is a challenging task. And this is mainly due to 2 reasons. The first one is that classical ab initio quantum chemistry methods are just very good for certain tasks. And this is a very old field, which is around since a long time, and they have very powerful algorithms to actually solve this electronic structure problem. The second reason is that the hardware requirements for quantum computation proposals for quantum chemistry, which are floating around in the community, are actually very difficult to reach in the near term. And this is very nicely illustrated by a figure which was compiled by the Microsoft Quantum team recently, where they actually analyzed how solving different types of problems on those quantum machines, how hard it is actually going to be to solve those problems. And it turns out that quantum chemistry is one of the hardest problems we can try to solve on those machines. So even with millions of qubits available, still runtimes of centuries could actually turn out to be the case for quantum chemistry methods. So it's hard to solve quantum chemistry problems on quantum computers. And today's talk is sort of trying to kind of overcome this kind of challenge or this limitation by trying to advance quantum chemistry and also material science in the near term by using state-of-the-art programmable quantum simulators and also really leveraging insights obtained from those very good classical quantum chemistry algorithms by focusing basically on well-targeted problems for those near-term intermediate scale quantum devices. And those targeted problems, the core target problem will be the thing, the Hamiltonian which is called the Heisenberg-Dirac-Van Vleck model, which is sort of a generalization of the well-known Heisenberg model in the physics community, where like it's a spin model where the spins can interact in many different ways, like in pairwise terms, higher order terms, but also they can be like the interactions can be highly long range and anisotropic. And in particular, the size of the individual spins in general will be larger than 1/2. And these spins 1/2 will now interact with a highly non-trivial interaction matrix. And it turns out that this model is quite a good model for multi-radicals, so molecules which have like atoms with lots of valence electrons, if those valence electrons are strongly localized to the individual sites. And here I have an example of a molecule which actually where this model works pretty well, which has like manganese atoms embedded in somehow an oxygen complex here. And for example, for this manganese atom here on the right, like some of those valence electrons are kind of bonded up with the surrounding oxygen, but there are 3 leftover electrons, and these 3 electrons will form a so-called active degree of freedom, which in this case is a spin 3/2 degree of freedom. And it turns out that figuring out the size of these spins and also the interaction with the spins at different sites is quite easy still using ab initio computational methods from quantum chemistry. But solving the full Hamiltonian and obtaining the spectrum, of course, is hard because it's still a spin model and the Hilbert space scales exponentially with system size. And as I will show in the following, this Hamiltonian has quite a natural mapping to quantum hardware, in particular to the employed Rydberg array platform, which we want to use. So in a sense, coming back to this original plot where I told you that quantum chemistry is very hard, we now try to not solve a full quantum chemistry model. We sort of rather want to solve a quantum dynamics problem where we actually use this target Hamiltonian and time evolve it and actually look at quantum dynamics of the system. And by doing so, learn something about the molecule. So based on what I just told you, we have like 3 core ingredients which we have to kind of engineer on the Rydberg array platform. We need to have a higher spin than 1/2, like not just spin degree 1/2. We want to have arbitrary connectivity between those spins. And of course, once we have this established, we also want to have an efficient readout mechanism to actually read out useful quantum chemistry information from these systems. And as I will show in the following, like we can actually implement these 3 necessary ingredients in a hardware efficient way by really using the unique properties of the Rydberg array platform, which is on the one hand, Rydberg blockade. The second one is that we can actually move atoms around, which I will show you in the following, allows us to establish arbitrary connectivity. And then one can take snapshot measurements after a certain evolution time and post-process them on a classical computer, which will result in an efficient readout mechanism. So let's start with this first ingredient, which we have to kind of engineer, which is finding a way to engineer high spin degrees of freedom. So for this, we envision placing a certain number of spin 1/2 qubits, where the qubit or the spin 1/2 is encoded in this hyperfine manifold of for example, rubidium, where we have 0 and 1, which is our qubit. And these qubits will also interact by van der Waals interactions because we can also like drive into a Rydberg state. And if they're like within the so-called Rydberg blockade radius, where we have a strong nonlinearity kicking in, they will like talk to each other very strongly. Just placing them within this kind of small radius, however, doesn't make them automatically a spin 3/2. To actually achieve that, we also have to lock them to the spin symmetric subspace, so the symmetric spin subspace. And this can be achieved by basically introducing an energy penalty for anything which brings you out of this subspace. And one Hamiltonian, which, for example, does that, like where basically the symmetric spin subspace is like the low energy space, is this kind of S² Hamiltonian between these spins. And to realize this Hamiltonian, now we have to find a global drive scheme for those Rabi frequency omega 01 and omega 1r, which can be time dependent, to actually realize the target unitary, which kind of evolves with this Hamiltonian. And to do that, we use optimal control techniques, in particular, the GRAPE technique, which stands for Gradient Ascent Pulse Engineering, to actually find those global drive schemes. And it turns out that such pulses exist, and they exist with very high fidelities, and they're like rather smooth and actually not like very, like one can actually like run them in a real experiment. And the most important part is, and that's actually the first point where the particular Rydberg platform comes in handy, the time required for one of those pulses as a number of qubits scales only linear, approximately linear, if we kind of actually allow like a very, choose a very restrictive kind of error, like of 10 to the minus 6, so 1 in a million. And then we kind of check how long does it actually take to kind of implement this target unitary for a certain number of qubits. So for example, for a spin 3/2, it would be like 15 approximately, probably flops sort of. If we now like restrict our error sort of limit a little bit, we find that in this case, if we just have an error of 10 to the minus 3, it hardly scales with system size, the time actually required to run this gate. And this is in very strong contrast to what would happen if we would decompose this whole sequence, this gate, into 2-qubit gates, which is what one would have to do on a digital simulator, where actually like the number of 2-qubit gates required to actually exactly sort of represent this unitary scales exponentially with system size. So on the Rydberg platform, due to the symmetric interaction with the Rydberg atoms, we have no exponential scaling with system size, which gives us an advantage over actually digital approaches in implementing large spins. So it is possible to hardware efficiently simulate high spins. So the first box can be ticked. Now we want to actually make these spins talk to each other and establish a certain interaction matrix between those spins. And to do that, now consider a certain geometry, like the one I depicted here, where we place individual spin 1/2 degrees of freedom in like clusters, as we see here, and like the number of spin 1/2 tells us what sort of large spin this cluster will have. So the first thing we will have to do is, of course, now lock all those clusters to the symmetric spin subspace, such that each of these kind of blocks is actually a large spin. And now to establish connectivity between those spins, we imagine like reconfiguring the entire array by kind of placing spins represent like spin 1/2 degrees of freedom representing different clusters next to each other, again within the blockade radius. And then we can apply sort of a 2-qubit version of this kind of gate with a certain right coefficient here, such that actually now the clusters will sort of know that they have to kind of be entangled or talk to each other. Then we can like reconfigure the system back and basically repeat this process many times. And it turns out, if we kind of run this sequence between these two different configurations many times, which implements sort of a unitary, trotterized unitary like that, for certain effective evolution times of HC and HI, this realizes a target Hamiltonian of this type, which is an S.S Hamiltonian with a general interaction matrix, which can be highly long range because we can also kind of take qubits and put them like very far from the original cluster and like make them talk, like make different long distance clusters talk to each other. And this realizes this target Hamiltonian on average to leading order, and then higher order contributions can actually be echoed out by using like more involved pulse effective evolution times for the individual two configurations, and using a particular symmetrized pulse sequence. And this sequence can also be tweaked a little more by basically taking changing the time this interaction Hamiltonian is applied. We also have access to like higher order term in this Hamiltonian, like not just S.S, but like basically these higher order term, like they actually in the 4K sequence, they appear quite naturally, but in our case, we can also switch them on by controlling the sequence. And that's important because these higher order terms are actually relevant for quantum chemistry in general, because they sort of are the first order corrections one gets from such a Hamiltonian if one takes local charge fluctuations into account due to kinetic degrees of freedom of the electrons. And we have quite a wide range of possible tunabilities of the different ratios of those terms. However, not arbitrary, of course, because this HI, this interaction Hamiltonian, like actually kicks us out of the symmetric subspace. And here the white region is the one where actually this leakage out of the symmetric subspace is like too large. I think we made a cutoff of 10 to the minus 4. But in here, we basically remain in the symmetric subspace under the evolution of such a Hamiltonian. So now we are able to actually establish connectivity by using this atom moving protocol on the Rydberg array platform. And this allows us to really establish a time evolution of this system. Now the big question is how do we actually use these tools? And this brings me to the third part, which is establishing sort of an efficient readout mechanism of chemically useful information using these techniques. And in terms of chemically useful information, we target two particular features, which are low energy states, so the low energy spectrum of the Hamiltonian, and then also finite temperature properties like magnetic susceptibilities. And we try to access these kind of properties by computing spectral functions, by using snapshot data of the experimental kind of state, so projective measurements at different times. And then we will post-process these data on a classical computer, and then as I will show you, we can actually get spectral information about the Hamiltonian, and not just ground state information, but actually like full spectral information. And this is because these snapshots are really information dense. They actually contain a lot of information about the actual states, the actual properties of the system at a given time. So to kind of walk you through this mechanism briefly, the core of the protocol are correlation functions of polystrings, in our particular case, like X string polystrings. And these correlation functions can be, again, efficiently kind of estimated by using kind of a circuit like that, where we kind of take an additional ancilla qubit now to help the time evolution sort of. And we initialize the entire system in the all up state. So all qubits will be in the all up state. And now we will perform a controlled perturbation on these all up states for all the qubits. And then after performing this controlled evolution perturbation, we time evolve the system by using this reshuffling plus global drive scheme I introduced in the beginning for a certain evolution time. And by doing so, we sort of, and then of course, in the end, we will measure the ancilla both in the X and Y basis and the system in the X basis. And by doing kind of such an approach, what we basically have, we compare the time evolved polystring versus the time evolution of the perturbed system, which gives us access to a correlation function at finite time t. And since these polystrings apply to this kind of up state, form a complete basis of the Hilbert space for our U1 symmetric Hamiltonian, and the all up state is actually an eigenstate of this Hamiltonian. All the information about the time evolved kind of perturbed state here can be obtained by kind of sampling over many different polystrings. And then after all, we also want to sample over many different perturbations. And if we do so, we can get like many of these correlation functions for different operators O and for different rotations R. And if we now average over many of them and then basically Fourier transform them, what we get, for example, for like just two spin 3 half particles, where we can very easily exactly diagonalize the Hamiltonian, which gives rise to this kind of vertical dashed lines here, we get a curve, which, for example, is this black one, which is the total spectral density for this Hamiltonian. And we see that this total spectral density has a certain width around those peaks. And that's just because the spectral resolution is kind of limited by the total evolution time, by decoherence processes in this evolution time, which is still an open system sort of, because it's like not a perfect quantum simulator. And this also leads to the fact that actually certain peaks in this Hamiltonian spectrum are missed. However, on top of what I just told you, we can also project down when actually doing this post-processing into the individual spin subspaces. And this gives us the so-called spin resolved density of states, which now only corresponds to kind of individual peaks around those energies. And this now also resolves certain peaks which are hidden in kind of the Fourier limit in this case. And if we now apply this technique to like an example molecule, like the one I showed in the very beginning, which is this molecule, which is part of this OAC complex, the oxygen evolving complex, and it provides electrons for photosynthesis by basically splitting water into protons, electrons, and oxygen. And this is a molecule we can still solve classically quite easily and get the spectrum, which are again these horizontal lines. And we actually see that this kind of total density of states or spectral density quite like actually captures the spectrum quite well. However, if we zoom in a little more, we see that there are certain energies which lie very close to each other, and the energy difference is very small. And of course, here again, our finite spectral resolution due to the finite evolution times we have available kind of washes out these kind of.
Stefan, you've had 20 minutes. So.
Oh, okay. Yeah. I will be done in a minute. Yeah, sorry.
All right. Mm-hmm.
Yeah. So now we can actually resolve these energies by kind of doing this projective measurement. And again, we have we can see that we can resolve them. And on top of that, we can now get chemically useful information out of such data, which is the, for example, the so-called energy ladder, which tells us which spin sector each energy state lies in. And with this, I'm actually at the end. So I showed you that all of these three main ingredients are possible to be realized on a Rydberg array platform. And here I will just like flash the summary of the protocol of taking strongly correlated matter, mapping it to a model spin Hamiltonian, which only takes active spin degrees of freedom into account, then mapping it onto a pro-model quantum simulator by using clusters of qubit, and then doing efficient state readout by using snapshot measurements. And with this, I also like there's an outlook, but I don't have time to go into it. And I thank you for your attention. Thanks.
Thank you. That was fascinating. Maybe we can allow one question or possibly two. I see Hongye has a question, I think. Please go ahead. Your microphone's off. Yeah.
Yeah, it's a very nice talk. So I was wondering, so is that possible to also include some like electron hopping in the future for the future work?
Yeah, I mean, that's a great question. And I mean, I have it down here actually in this kind of extension outlook. I mean, this Heisenberg type model is actually like just a starting point, and it captures a certain but still small set of materials and molecules because we require the electrons to be localized around the individual sites. And I think the next step is exactly as you're saying, like including kinetic degrees of freedom. And this model one would consider there are so-called TJ models. And of course, then after all, one also would want to have like fermionic degrees of freedom. And that's like exactly the future direction we want to take, yes.
I think Alexei has a question.
A quick one. I'm curious, what's your take on analog versus digital? What are you going to push for?
Yeah, I think the approach I sort of presented is like there is some certain analog aspect, which is in particular this global drive to implement the high spins, and the rest, like this Floquet engineering, it's rather digital. So it's actually like we have gates and we'll apply them in a sort of digital fashion. But I think, as I showed actually in the beginning, I won't go there, but so I think certain like analog simulators in certain ways have advantages just because they have like more general, like basically like digital approaches, like qubit-based, solid state-based approaches, for example, like on the Google machine, they have like a very kind of restricted connectivity. And that's the big advantage, like for these problems here, that in principle, we can have arbitrary connectivity between our qubits. And that's like, I think why this is like more hardware efficient than doing it on a purely digital solid state-based machine, for example.
Okay, it'll be lovely to continue the discussion, but I think we need to move on. So we'll move on to the second talk, which is given by Hongye Hu, also from the Harvard University Department of Physics, and the title is Analog Quantum Learning from Quantum Simulation. So please go ahead.
Okay, thank you for the introduction. I'm Hongye from Susanna Yellin's group at Harvard. Today is really my honor to present our recent progress on analog quantum learning for quantum simulation. See, over the past few years, we have witnessed great progress made in artificial intelligence, and it reminds us the way and the ability of human to process information are important milestones that marks the human civilization. So in the past, we have utilized mechanical tools and electronic tools to do the computation. And entering the 21st century, we have seen a new dimension of computing, which utilized quantum mechanics. Despite the fact that there are many provable advantages in the quantum algorithms, the fault-tolerant quantum computation is still very challenging. So that inspired people to ask the question, can we use variational method to solve problems with the near-term quantum devices? And this question basically inspired the field of quantum machine learning. And depending on the type of algorithm, which can be quantum or classical, and the type of data, which can also be quantum and classical, the field of quantum machine learning can be characterized into 4 parts. So the first part is a classical algorithm for the classical data, for example, the quantum-inspired classical neural networks for classical image processing. And the second part is a classical algorithm for quantum data, for example, the classical neural network for these quantum simulations. And also the third part is a quantum algorithm for classical data, such as use the quantum neural network. And last but not the least is the quantum data and the quantum algorithm, which is also called variational quantum simulation. For example, people have proposed to use that to solve for ground state property, quantum dynamics, excited state, quantum metrology, etc. So in this talk, I'll mainly focus on the last part, which is the quantum algorithm for quantum data. So there are 3 key components in the variational quantum algorithm. The first one is the quantum answers. So like the classical neural network, which utilize the parameterized continuous function, in the quantum answers, we have a parameterized quantum evolution. For example, those gates can have certain parameters, or the Hamiltonian can have certain parameters. And the second component is the cost function, which is the objective that we want to minimize in order to achieve some task. And usually we measure from the quantum computer to have an estimation of the cost function. And then that leads to the third component, which is a classical optimizer. And based on the measurement of the cost function, the optimizer tells us what are the updates that we should do in the next time step. So in this talk, I'll address 2 of the challenges of the variational quantum algorithm. The first one is the noise. So due to the noise, it prevents us from running a really deep circuit. So we ask the question, can we use some classical method to achieve an entanglement reduction, such that we can use a shallow circuits to do the same thing? And the other part is the measurement issue. So measuring cost function is really hard, and we ask the question, can we design some better protocol? And we'll see that with randomized measurement, we can predict those quantities very efficiently. So a fundamental goal of the electronic structure problem is to solve for zero and finite temperature energy of this many-body interacting electronic Hamiltonian. So here is the first quantized Hamiltonian. We have kinetic energy, electron-nuclear interaction, and the electron repulsion. So the first thing that we want to do is that we need to translate this first quantized Hamiltonian onto a qubitized Hamiltonian, such that we can use the quantum computer based on qubit to simulate that. And the first step is to invoke the classical method, which is also called a Hartree-Fock method, to solve for those molecular orbitals. And those orbitals can be viewed as a basis in the real space. And with those new bases, we can translate this first quantized Hamiltonian into a second quantized Hamiltonian, where this A dagger and A are the creation and the annihilation operator for the fermions. And then we can use some fermion to qubit mapping, such as Jordan-Wigner transformation, to further translate these fermion operators into a qubit operator. And with these 2 steps, we basically translate this first quantized Hamiltonian in real space into a qubitized Hamiltonian, which can be expressed as a polystring. And with that, it's very tempting to use the quantum computer to solve for the ground state energy, for example. And here is the experimental data I stole from the IBM paper. basically simulated the ground state energy of this beryllium hydride. And even though they optimize all the parameters theta on a classical computer with very high accuracy, we do see that in experiments, due to the noise, there are still a finite energy gap. So that inspired us to ask the question, so if their circuit have some noise, can we reduce the circuit depth and achieve a better performance? And more fundamentally, we ask the question, after this translation, we have a cubitized Hamiltonian. Are all the entanglement in this cubitized Hamiltonian intrinsically quantum, or can we use some other classical method to further reduce the quantum in this Hamiltonian? The first observation is that entanglement doesn't equal to quantumness. For example, I can have a highly entangled quantum Hamiltonian. So here I used the Torrey-Colt Hamiltonian as an example, which possesses the long range and non-trivial entanglement. But nevertheless, I can find a simulable quantum circuit to transform this highly entangled Hamiltonian into a classical Hamiltonian. So this simulable quantum circuit basically achieves this entanglement reduction. And in general, we want to ask the question, can we use some simulable quantum circuits as another layer of the classical method to further reduce the entanglement in the target Hamiltonian, such that the effective Hamiltonian have some intrinsic quantumness that we really need a quantum computer. And the simulable quantum circuits we focused on in our work is Clifford plus a few T-gates answers. So first of all, the Clifford circuits are generated by the Hartmann gate, phase gate, and the C0 gate. And it can be simulated with classical computer in polynomial time. And moreover, what makes Clifford circuit special is that it can generate very rich entanglement. For example, this long-range entanglement and volume law entanglement. So Clifford circuits alone is not universal because we can simulate that with classical computer. What makes it universal is by adding more T-gates. So the T-gates will make Clifford circuits universal, and the classical simulation complexity will scale exponentially with respect to the number of T-gates in these answers. So the goal is that we want to use Clifford plus a few T-gate circuits as another basis transformation upon this Hartree-Fock method to further reduce the entanglement in this cubitized Hamiltonian. In other words, we are searching for an interior basis transformation in these answers, such that after this transformation, the effective Hamiltonian is very close to diagonal. So originally, we may have a very highly entangled quantum Hamiltonian, but after transformation, this effective Hamiltonian is reduced. And what is the leftover entanglement in this H effective is gonna be intrinsic quantumness. And we apply this idea to the zero temperature and finite temperature quantum chemistry problem. So from another point of view, these basis transformation can also be thinking as like adding a virtual quantum circuit to these real quantum devices. And this virtual circuit is executed on a classical computer. So we basically deepen the circuit depth, but didn't introduce any quantum noise because it's a classical simulable. And another very nice feature of our answers is that we have a good understanding of the hierarchy. So first of all, the classical Hartree-Fock method solution in the qubit basis is a product state, and the Clifford circuit can generate those Hartree-Fock solution. And moreover, these Clifford circuits can generate fermionic interactions. So this basically gives you a proof that these Clifford answers alone will be strictly larger than the classical Hartree-Fock method. And by adding more T-gates to the Clifford circuits, we are expanding the expressibility. And this yellow region is what can be classical simulated. So this is the classical simulation limit. And the gap between the full quantum and the classical simulation limit is the entanglement cannot be simulated classically and cannot be reduced. And that is what people call the quantum magic. And the quantum magic is what people really need a quantum computer for. So we apply this idea to the ground state energy estimation of the lithium hydride. So here is an example. We basically use a classical computer to search for the basis transformation and have this H effective. And we evaluated the expectation value of this H effective on a product state. And we plot the energy gap between this value with respect to the true ground state energy of this lithium hydride. So the first observation we see that is theoretically we know Clifford answers will be strictly better than Hartree-Fock solution. And this light blue line indicates the pure Clifford circuits where the K equal to 0. And we see that when the bond length between those two items is small, we didn't see any improvements. But as we increase the bond length, we see it achieved the entanglement reduction, and actually Clifford transformed solution is better than the Hartree-Fock solution. And moreover, when we add in a few non-Clifford gates, when this K equals to 1, 2, 3, 4, we see that the energy gap reduced dramatically. So this is on a log scale. So that is quite nice. So another interesting feature we observed for many different molecules is that the non-monotonic behavior of this energy gap. So as we see in the abundant small and large region, we can reduce the entanglement quite large, but in the middle around the 3, we have a peak. So this is the indication that there are like intrinsic quantum needs at this bond length. And to verify our understanding, we calculate the stabilizer range entropy, which people use to quantify the quantum magic for the ground state and the first excited state of this molecule. And for these black lines, those are the results. And we do see around bond length around 3, the quantum magic basically have a peak. So that is an indication at these bond lengths, it's really hard to reduce the quantum entanglement with any classical simulable circuit. And what we really need is the quantum computer. So basically, with that, we also simulated readable atom chain as our physical hardware to further estimate the ground state energy and generate some quantum magic. And in our answers, we fixed the atom position and the total evolution time. What can be optimized are the Rabi frequency and local detuning pattern for each of the items. And here are the results we evaluated on the original cubitized Hamiltonian and our transformed Hamiltonian. And we see when the total evolution time of this quantum system are equal to 0.1 microsecond, which is really short. The physical hardware doesn't generate a lot of quantum magic. So the performance is really bad of the original Hamiltonian. It's even worse than the Hartree-Fock solution. But for the transformed Hamiltonian, nevertheless, it's guaranteed to be better than the Hartree-Fock solution. And as we enlarge the total evolution time to 0.25 microseconds, we see a lot of results with transformed Hamiltonian are already achieving a really good estimation of the ground state energy. However, if we just use the bare Hamiltonian we have in quantum chemistry, it just outperforms Hartree-Fock very marginally. So this figure shows that by this entanglement reduction, we can shorten the evolution time of our physical hardware, such that we don't need to evolve our devices for a really long time. And the same phenomena will also hold for the finite temperature simulation, which I'll not expand here. So another challenge in the original quantum algorithm is the measurement issue. For example, measuring the cost function is not very easy because we have multiple poly that we need to measure. And more fundamentally, reading quantum information is a hard problem. For example, a quantum tomography is exponentially hard. And over the past 2 years, exciting progress have been made on the randomized measurement, or also called classical shadows. So first of all, this randomized measurement protocol is tomography complete, meaning that in principle, we can predict the arbitrary quantity of the underlying quantum state. And moreover, it has a provable efficiency, meaning that we can predict exponentially many properties with only a few measurements. So here, to give you a sense how powerful this is, we estimate the quantum fidelity, which is exponentially hard problem for the traditional measurement protocol. However, with randomized measurement, if we use 1,000 shots to estimate fidelity of a 10-qubit system, we can also just use 1,000 measurements for a 50-qubit system to estimate the quantum fidelity, which is quite amazing. So as a bird's eye view, the randomized measurement consists of 2 parts. The first part is a random quench evolution of the underlying system. And then after evolution, we take a computational Z-basis measurements. And then with this computational Z-based measurement, we need to do some post-processing in an unbiased way to give the prediction. So the challenge of the original proposal of classical shadow is that the unbiased post-processing method is only known for two limits. The first one is a zero entanglement limit, where people just use a random single qubit gates. But for this protocol, there is no advantage in predicting non-local properties such as fidelity. And the other limit is a very deep circuit limit, such that it have an exponential advantage in terms of predicting non-local properties. However, the very deep circuit is very experimental challenging. And in the middle of this spectrum, people don't know how to do the post-processing in an unbiased way. And our method, our contribution is that we provide this unbiased formulation to post-process the data for a large class of these randomized measurements based on the so-called local scrambled quantum circuits or dynamics. And here I just give 3 examples to show how versatile this new protocol is. So first, it can be applied to shallow circuits with arbitrary circuit depths. It can also be applied to a fixed unitary evolution toward by the single qubit gates. And last but not least, it can be applied to this random quench dynamics. So in the last slides, I want to show you results on using the programmable quantum simulator to generate some entanglements in this randomized measurement and to predict quantum fidelity. So here is we used 1,000 shots for the fidelity estimation. So these blue dots are the traditional method. And we do see that if we have more qubits in our underlying system, then the error bar grows exponentially, which is expected. However, if we use the programmable quantum simulator to generate some dynamics and then do the randomized measurements, these results in the green line, the green dots, we see that the error bar almost doesn't grow. So this is an advantage of using these shallow circuits or some quantum evolution in the randomized measurements, such that we can reduce the sample complexity a lot. So with that, I'll conclude my talk. So in the first part, we touched how do we use simulable quantum circuits to achieve entanglement reduction and effectively reduce the circuit depth or evolution time. And in the second part, we talked about how to use shallow circuits or coherent dynamics to do the efficient tomography, which is considered to be a really challenging problem traditionally. And with that, I'll thank all my mentors and collaborators, and also thank you for your attention.
Thank you very much. Nice talk. As chairman, I'm going to ask a question here. I'm an experimentalist. I mean, how advanced are the Rydberg systems? I mean, how close are you to doing this in the lab with Rydberg atoms?
I see. So for the first part, this one, we only require the local control of the Rabi and the detuning of each of the items. I think currently that's already experimentally feasible, at least in the laboratory. I know that's feasible. And for the second part, when we use the programmable simulator to reduce sample complexity, this fixed unitary evolution can be anything. At least as long as it can generate entanglement, it will be better than doing nothing. So this one can also use global pause, for example, that is also commercially available. So that's I think for both of the protocol is experimental feasible. Yeah.
Okay, thank you. So other questions, anyone? We have 1 minute, I think. I don't see any.
Yeah, I have
you go ahead.
Actually, yeah. So Hongye, if you go back to this number of T gates, how the energy gap goes down, it seems as if it doesn't get much, there seems to be some convergence there. Is this correct, or what would you expect if you now have 10? So is there some boundary at some point, which you hit? First there's a big effect, right? And then it gets smaller, sort of. So do you think that this will saturate at some point?
Yeah, that's a great question. I think for so this seems to be converging. It's an indication that when we only use Clifford circuits, we cannot reduce the entropy anymore. So what is left over is something that is really quantum, is intrinsic. People also call that quantum magic. So for that, I think, yeah, we do need a quantum computer. And maybe, we don't have K equals to, for example, 20, because that's really hard in simulation. But yeah, it seems to be an indication that at some point we can just not reduce it by the classical simulable circuits.
Okay, I think thank you again. Thank you for a nice talk. And let's move on to the next talk, the third talk.
Thank you.
Which is to be given by Han Kai from the College of Optical Science and Engineering at Zhejiang University in Hangzhou in China. And the title is Quantum Simulation with Superradiance Lattices. So please go ahead.
All right, thanks for the introduction. First, I want to thank Dr. Hammer and Dr. Sokolov. They used to be my teachers in NN, and I really missed a great time in Texas. So it gives me an opportunity to share with you our recent work in quantum simulation with a specific platform. We call it superradiance lattices. So the outline, I will briefly give a briefly introduction about the motivation and what is superradiance lattices. And I will try to use some example to persuade you that it is interesting in some aspects. And here is my principal collaborators from the same university, Dawei Wang and Xiao Zhu, and some other domestic and international collaborators. So, yeah, we all know that Feynman and Manning, they mentioned that we need to use a quantum system to study the quantum problem when it's beyond the capability of a classical computer. But of course, the ultimate goal is that the general purpose quantum computer. It is highly competitive fields. But at this current stage, we are still in the quantum simulator that we aiming to solve some specific problems, like the two very excellent talks, the previous talks, like they aiming solving some quantum chemistry, the ground state. Here I want to we aiming to solve some study some exotic novel physics matter. For example, the graphene. We know we have two layers and we twisted them. We have the magic angle, like the Mori pattern and superconducting. Yeah, we can, on the other hand, we can simulate such kind of Mori physics with, for example, optical lattices. We use two layers of optical lattices and twist them a little bit, and we see the pattern showed up and some kind of physics. Now it's a very highly it's a very highly competitive field. A lot of platforms, candidate platforms like the optical lattice, and of course the Rydberg atom array, ion traps, and the semiconductor quantum dots and superconducting circuits. So if we already have such kind of real material, why we still trying to simulate it? The problem is sometimes the real material, the electron in the solids, the lattice constant is very small, and the time scale is very fast. So the microscopic dynamics or the spatial resolution is very difficult to get clear. So the straightforward way is that we localized or trap some atoms, especially periodically, to form a network, and we form some hopping between sites, and here is some two examples, famous models, the Hubble model or the EC models. So yeah, of course, here we're aiming for the atomic systems because they are some good candidates. They are identical anyway, and the interaction between atoms are easily to tune. But they also have problems, the very popular platforms. And of course, you need to trap the atoms, especially periodically. So it means the low temperature. So, but sometimes for the exotic phase of matter, you need to strongly modulate it, for example, flow rate modulation, or to apply some effective field, electric field or magnetic field. So it will heat the systems and introduce some thermal noise. So our goal is to find some thermal noise resilience. Is it possible to find such kind of platform? Here, this is my major motivation for this talk. So I will introduce the superheated lattice, which is an atomic platform in room temperature, and we simulate some interesting, simple but interesting phenomena in the condensed matter physics. So first, I will introduce the basic bricks of the lattice. That's the site. Each single site is we call it timed decay state. Just imagine we have a bunch of atoms, two-level atoms, and they're randomly distributed like the atom vapor, and we inject one single photon, and this photon will be absorbed by the atoms. And because the photon propagating, it will have a phase, propagating phase, but different atoms sees the photon at different times. So the phase of the photon will be mapped to the final state. The final state will be a spin wave state, and even it is a single excitation state. And this final state will be characterized by this phase correlation, which the wave vector exactly equals to the photon. And this state is highly studied by my advisor, Dr. Scully and Dr. Swinzinski. They find that even there's only one excitation, single photon, and we still have some cooperative effect like the directional emission or the enhanced decay rate compared to a single atom. So imagine we have a lot of collective state. They have different phase correlation, when they oscillate faster and faster. And because the phase correlation are defined by the wave vector, and all these states, we can use the wave vector to define them in momentum space. And if we can switch the phase between these states one by one, we collect all these states in momentum space, forming a tight binding model. And we have two very special states because their phase correlation phase match with the vacuum. So they will have the directional emission as I mentioned in previous slide. So that's the major way we read out the information of the lattice. So how can we switch the phase? Imagine we have a single photon for these three level atoms, and we prepare a time decay state with K momentum, and we can have a high pulse coupling, very strong coupling field, but with high pulse area to have the stimulated emission to drive to read out to get the photon out. And then because the atoms see the coupling field at different times, so their phase will be exactly canceled out, leaving out the zero momentum. And then we can have another counter-propagating coupling pulse to drive the system back to the excited state. Now the system will have a less momentum, minus K. So imagine we have the pulse trend, the pi pulse trend, that we can connect all these states one by one. And if we have a standing wave, then we simultaneously just connect the whole all the states in momentum space to forming a tight binding model. Okay, this is the external setup. It's a very simple one. We have a standing wave, coupling wave to passing through a rubidium cell, or this is thermal cell, and rubidium atoms flying in there. And we just use the prop field to detect the optical response. And this is the absorption spectrum of the prop field indicates the density states of the lattice. There's other viewpoint to see the lattice. We can see this is a standing wave coupled atoms. because the standing wave, it has the field strength is modulated in space. And we know the atoms are splitted by due to the Atlas-Tower splitting. The energy level of atoms will split by the field strength, and we can write the Hamiltonian in space, which is the off-diagonal term is exactly the spatial modulated field strength, and the O omega is the right frequency. When you see this Hamiltonian, it reminds you the Hamiltonian of a one-dimensional tight band model in its reciprocal space. But we just need to change the omega to the T, the Hopper stress T, and switch the kx and the real space and momentum space. And that explains why we have a momentum space lattice. Now the atom thermal motion enters. It actually it gives a very simple formula for the coordinates of atoms, because the atoms are moving, so the atom coordinates increase linear in time. But when you switch the x with k, as I said in previous slide, it simulates a non-trivial phenomenon. The crystal momentum of the Bloch electron in solids will increase linearly in time. It means the Bloch electron feels a constant force, like the static electron force, and drive the system to behave Bloch oscillation. So that gives us the hint that the atomic thermal motion is only equivalent to the effective static force, and the force stress is proportional to the velocity of the atoms. And it also have a gift that we have the closed trajectory around the brilliant zone for free, since we have the brilliant zone in real space and the atom just traveling in free real space, so that we have the closed trajectory. So it has some many interesting consequences. Like first is the Bloch oscillation. We can easily calculate the period of Bloch oscillation, because we get the period is the length of the standing wave divided by the velocity of the atom, and we can get the frequency of the Bloch oscillation. In experiments, we can measure the absorption spectrum of atoms with different velocity. We notice that when the velocity of atoms increase, their absorption spectrum splits into discrete levels, and that's exactly the signature of periodic oscillation, and their distance is equivalent to the frequency of Bloch oscillation. And we also notice when when we measure the atoms with zero velocity, we have we characterize the density states of the band. Now we have two peaks, and these two peaks corresponding to the band bottom and the band top of this very simple band structure. And we also measure the same phenomenon in ultra-cold atoms with our collaborators to eliminate the result of thermal motion to justify our theory. Another interesting consequence of the closed trajectory is that gives us a new method to measure the Z phase. We know the Z phase is the geometric phase. When you take a closed trajectory in parameter space, for example, in this sphere, when you move this vector adiabatically, very slowly, you don't introduce any local rotation of the vector. But when you do it on after a closed trajectory, it still rotates a little bit, and the rotating angle is proportional to the solid angle it covers. So this concept is useful in many aspects of physics, and in condensed matter physics, it means we know on the left and right side of brilliant zone, it is the same point. So when the electron have Bloch oscillation, it will accumulate the phase. It called Z phase, directly proportional to directly manifests the geometry of the band. And you can imagine how difficult to measure it. You have to prepare electron. You have to, for example, in the ultra-cold atoms, you have to prepare the ultra-cold atoms with very precise momentum, and you have to adiabatically drive it through all the brilliant zone. And you have to do the interferometry afterwards, and you have also need to care about how to eliminate the dynamic phase. But our results give a very natural way to read out the Z phase. Now the Z phase, for example, now we have this two band structure with gap, and for each band you have the when the atoms do the Bloch oscillation, you have discrete levels, and now you can have the Z phase from the slope of the discrete peaks, and it gives the spectroscopic way to get rid out the Z phase of our synthesized band. We take a very the simplest topological insulator, for example, the SSH model for the V. It only characterized with two parameters, V and W. V is the inner cell hopping, and W is the intercell hopping. When V is larger than W is one topological phase, and otherwise it's the other. When they equal, that's the topological phase transition. It's very easy for us to synthesize the SSH model. We just need to tune the relative strength between two Rabi frequency, because the Rabi frequency is the hopping stress in our model. So we just tune the relative strength between two counterpropagating waves, and we have two different topological phase and the phase transition, and we measure the slope, which exactly give us the right result. We have the 1.5 Z phase and the 0.5 Z phase for these two topology phases, and for the phase transition, we have theta equals to pi. We can also generalize to more we can also generalize to Rice-Milling model, where the Z phase is either integer or half integer, and which give us a very good agreement with the theory. And we can also play with the laser configuration and the energy level. For example, for a 3-level to 4 levels, we can play with the structure to simulate a lot of different lattice structure. One interesting application is that we can also propose a new way to measure the Chen number. We know the Chen number is usually can be measured by the quantum Hall effect or the anomalous transport. But here we can just measure the Chen number by measure different trajectory for this two-dimensional band. We cut the two-dimensional band with different trajectory along these control parameters, and then we measure all these different Z phase. And the widening of Z phase around this direction, characterize the Chen number. When it's wide 1 times, that's equals to 1, otherwise it's 0. Long time ago, we already proposed how to simulate the Howden model in the superior lattices. We introduced flow-quick modulation, and here we give some brilliant result. We can measure different. We can measure the Z phase with different position, and measure how they wide along one brilliant zone, which gives out Chen number with one widening, or no widening, which means Chen number is 0. Here is some brief introduction about we can also simulate the synthetic gauge field or the flat band localization with our scheme. The last interesting example I want to show is that we can do the flow-quick engineering of superior lattices, which we can strongly modulate the lattice without any heating, because our system is already thermal. We introduced the modulation of a system by using TEOM to introduce a dynamic phase of the Rabi oscillation. So that's effectively introduced an AC field along this lattice. And we characterize the transport from this site to this site by measure the reflection spectrum of the probe, because the reflection intensity is proportional to the distribution on this site. And when the system it is known that when the one-dimensional lattice is driven by a strong AC field, the band can be collapsed. So when it's collapsed, the transport of the electron will be completely stopped. So it has been simulated in ultra-cold atoms or some waveguide arrays. Our system can have a very rich phase diagram of all the different phenomena, like the without AC field and the DC field. This is the original lattice. We can have a very strong transport. The color scales the transport. And when we have a very strong AC field and the field, the parameter meets the 0 point of a Bessel function, the transport
excuse me, you've had 20 minutes, so if you could just reach conclusions.
Okay, it will be stopped very soon. So now we can have the stack localization. Well, if we have both AC DC field, it will transport again. Then we have the dynamic delocalization. So that's basically the end of my talk. And thank you very much.
Thank you. I wish there was more time. I'd have lots of questions for you, but I maybe one question from someone else, if there is one, because we're really a bit behind in time. Anyone have a question? And I guess there's a very close link between this work and topological states on photonic crystals and so on. I mean, it seems like that's the case.
Yeah. All right.
Anyway, okay, thank you. Let's move on to the next talk.
Thank you very much.
Yeah, thank you. The next talk is by Philip Hemmer from Texas A&M, as I mentioned already, and there's another address, the Hagler Institute for Advanced Study in Department of Physics and Astronomy. It's very long, you can read it. The title of the talk is Engineering Nanodiamonds for Quantum Sensing, so please go ahead.
Okay, so can you hear?
Yep.
Okay, good. So hopefully you can see the screen well, because it's doing something funny at this end. Okay, so engineering nanodiamonds for quantum sensing. So this is an experimental project, basically reporting on what we've got, the recent results we have on trying to make nanodiamonds perform the way they're supposed to. Okay, so I acknowledge all my collaborators, mostly this collaborator. Oops, if I can make my pen show. Mostly my collaborator from Saudi, but others also. Okay, so the idea is if we take diamond, what sensors do we normally use in diamond? Okay, well, normally we use something like the nitrogen vacancy. Okay, the nitrogen vacancy is basically a vacancy, so an absence of a carbon atom and a nitrogen atom adjacent to it. The big advantage of the nitrogen vacancy is it can sense magnetic fields. Okay, and then how does it do this? It does this by having its fluorescence level change depending depending on the spin state that you're in. So, for example, if you're all in the ground spin state, you get a certain level of fluorescence. If you mix these, then the fluorescence goes down. Okay, that's a fairly simple idea. And then, of course, these are Zeeman states. So if you apply a magnetic field, then you'll get Zeeman splitting, and that'll give you magnetic sensing. Okay, so if you want to decide how well these work, the key thing is this percentage change in the fluorescence. Okay, so for the nitrogen vacancy, that's about 30% for a single. If it was any less than that, probably nobody would be so excited about it as they have been over the years. If it was more, then a lot more would have been done, and things would be much farther than they are. Okay, so let me first kind of review what's been done with the nitrogen vacancy. So the first experiments we did was to try to detect a spin label outside of the diamond lattice. And the idea there is we basically created some kind of a pull sequence for the nitrogen vacancy that allows us to detect the magnetic field. And then we put a resonant drive onto a spin label, which in this case was an electron spin, a nitroxide. And then you change the orientation of that spin, and you can see its effect with the nitrogen vacancy. You can see the magnetic field changes. And we were able to get near single spin levels, or near single spin detection. Fast forward about 15 years, and it's still more or less the same way, except now that spin label is on a protein, and you can get some conformational changes by doing this measurement. Okay, and since then, the last 5 or 10 years, it's kind of slowed down. It hasn't really been moving as fast as I would like, and the reason is partly because of this problem I told you with the percentage in fluorescence change. It really needs to be bigger. So it turns out that there are other color centers in diamond, and some of them have bigger changes in fluorescence. So here is one called the ST1, and it's a positive change in fluorescence as opposed to a negative. So the advantage of that is that your background can be essentially a much lower noise level, and so you have a much better chance for single shot readout, which is going to help you a lot on sensitivity. Okay, for a long time, people have been trying to identify this color center. Recently, it's been shown that it's related to the oxygen vacancy, and that is a pair of oxygen vacancies with some separation. They're not adjacent, but they're not too far apart. Exactly how far is not known. And in fact, if you look at a crystal which has a lot of these, and you look at ensemble measurements, you find that there's a lot of magnetic resonances at many different frequencies, and what you'll find is that they can either be positive or negative. So this is the typical that people see for the ST1. They see a positive optical change as you hit the microwave resonance. But in this particular crystal, if you go to a different location, you can get a negative negative ODMR, or negative magnetic resonance. If you put a magnetic field, then you get all kinds of interesting stuff. You get some positive and some negative, and some of them don't show up at all without a field, and some show up very strongly. But always you can sort of see that in one region, they're one sign, in the other region, they're the opposite sign. And so there's several different color centers here, and we don't know how much of each one, but there's several different ones. And the key thing is, with a slight change, you can go from positive to negative. Okay, so what do you expect positive ODMR? If your ground state is singlet, then you're going to get positive ODMR. If your ground state is triplet, you'll get negative. And so we have a situation here where just a short distance apart in the crystal lattice, the ordering of the ground state changes. And so one of the reasons to explain that is that these singlet and triplet levels are almost degenerate. And a very small change to the lattice is enough to make the difference. And that implies that these oxygen vacancies are not adjacent, which is, of course, what we found out already, and that they might be quite far away. And so this is actually quite important for sensing, as I'll talk about later. All right, so now I remind you that everything been done so far has been done in a bulk diamond, and you put the system you're trying to image on the bulk diamond. And the reason is because, bulk diamonds have very good properties. But of course, you want to shrink this down, okay? The size makes a big difference. If you're detecting a molecule, say in a biological system, you don't want a probe that's bigger than that molecule. You want something small. You don't want anything to interfere with the function. So if we look at the different fluorescent probes, there's a rhodamine dye, and this is the most popular biological probe, is a green fluorescent protein. Okay, in between here is the smallest diamond with a fluorescent color center. This comes from a meteor. It's basically a silicon vacancy and a very small diamond. Okay, and so what we want to do is we want to make more of these. We want to be able to produce these ourselves. So let's look at how nanodiamonds are made so far. Okay, the best ones that are out right now start with a large press that makes a big crystal of diamond. Okay, then you take that big crystal and you break it up into small crystals with a milling machine. When you're done, you have this agglomeration of all different sizes, all different shapes. They have sharp edges, they have damage. And so basically you've taken this high quality material, which is the bulk, and you've ended with a low quality material. But that's the best so far. So what other techniques are out there? Well, detonation is quite popular. There's the detonation of explosives, there's ultrasound, and there's laser ablation, which are very similar processes. These tend not to make high quality because the growth is happening in a very short time, in microseconds or so, and so there isn't really enough time to get a good crystal lattice. There's also some work on plasma or CVD. These are high quality. You can get very good quality nanodiamonds, but it's inherently a surface growth technique. And so if you want to scale it up, it's going to be complex. It's possible with a flowing plasma to scale it up better. And I've done some work with these, and there's actually, you can get some promising things, but they're difficult to control. Okay, so what we've chosen to do in the last couple of years or so is to use high pressure, but not those big presses. We've chosen to use something very small, basically a diamond anvil cell. The way this works is you have two diamonds, one here and one there, and they have sharp points, which have been slightly flattened, and you put a metal gasket between, and you press it. Okay, and that gives you a very high pressure inside. Now, the advantage of using this diamond anvil cell, one of them is that you can look through these diamonds. These diamonds are transparent, as you can see inside. So here's the top view, and you can see down inside of the hole in the gasket, and down in there you can sort of see what's happening as things are changing. So this particular experiment, we heated up some paraffin, and crystals of graphite started to grow from the Inconel gasket. And so the idea is you can see interesting things go on. The disadvantage is basically a small volume. Typically, these are nanograms. And so you have, after you do a good experiment, you get some good growth product, you have enough to look at it on the microscope and verify that you have something interesting. But if you want to send it to somebody else, there isn't enough. And so we need to really get this problem solved. We need to get a lot more a lot more volume. The other problem with the diamond anvil cell is it's a diamond, so if you want to grow diamond, the Raman line of the anvils kind of covers up any Raman line of the product that you're hoping to get. So let me just give you another example of what you can do when you have this diamond anvil cell. This is the Raman spectrum of adamantane, which is one of our precursors. As you you shine a laser and you heat it up, as you increase the power, you can watch you can basically watch the changes in the CH spectrum. Okay, so you can see, you can watch the source material getting consumed, and unfortunately you can't see the diamonds being produced, but maybe we'll solve that a little later. So this is sort of what happens. You get a lot of control in this diamond anvil cell. And one of the things you can do is you can control the growth temperature. Okay, so here at growth temperature of about 1700, we get nitrogen vacancies, okay? And we get these even without irradiation or anything else. However, there's a lot of nitrogens in the lattice. You can see by looking at the magnetic resonance spectrum, there's a fairly large zero field splitting, and the amplitude is pretty low. So even though these were growing at high pressure, they're really not especially at the high quality that we're looking for. If you go a lower temperature, then you can get silicon vacancies, even without the radiation and annealing. You go still lower, and silicon will not go into the lattice at this temperature. Nitrogen still will, but now you have to irradiate and anneal, and you get much better magnetic resonance in the sense that splitting is very small, okay, but it's not quite small enough. You go down to very low temperatures, and you get essentially very few nitrogens. You get no observable splitting in the magnetic resonance. You get some charge instability, which says that you have no other donors in the lattice. And so just by changing the temperature that you grow, you can drastically change the properties of what you get in the diamonds. Okay, and so what we have to do is we have to grow as low a temperature as possible to get the good quality and exclude all the impurities, but we want the impurity that's going to give us the color center. And so we have to separate out the nucleation process from the growth. So what we do is we take a seed molecule, which looks like a diamond, we put in our dopant, and then we grow pure diamond around it. We grow at a low temperature. Okay, and so the idea then is that if you only get this one impurity in, well, that's all you need because it's surrounded by high quality diamond, and then you'll get much better performance. Okay, so that's the basic idea. We've done some preliminary experiments with that. We did a seed molecule that has 2 nitrogens. So this is not expected to make nitrogen vacancies. In fact, we don't see any. If we grow at a high temperature, this molecule breaks apart, and then we do see nitrogen vacancies. We see exactly what we expect. And so this seeding approach is doing something. It is in one case giving us nitrogen vacancies, in another case not. And this is quite interesting because at this temperature, basically nitrogen doesn't go in the lattice no matter how much you have. We have a lot of nitrogen in the growth mix. So now that we can imagine doing this, we took the first step towards growing a quantum computer, and that was to get a lot of these seed molecules attached together on the polymer, and we try to grow a diamond around that. Well, we have very different looking crystals than we got before, but we need to get nitrogens into this to look at NVs. And so that's something that's actually, we've actually in progress now, and we're getting some progress on it. Okay, so one thing we have to address in making these nitrogen vacancies, the same problem that people need to address in scalable quantum computers. If you want to make a scalable quantum computer, you need an array of coupled NVs. However, in the real case, when you implant them, you get very few, and that's because the probability of each nitrogen that you implanted, the probability of that turning into NV is really small. It's like a few percent. So you need to bring this up past 50%. Okay, so recently there have been some experiments showing that doping with things like sulfur or maybe oxygen will give you a very high yield. In other words, the typical you're talking a few percent with intrinsic diamond. So if you look at the NV creation yield, in this case, a few percent for this particular implantation energy. If you put sulfur, that jumps up an order of magnitude. Okay, so now instead of, in this case, it was 7% for this step, now it's 70%. So now you can imagine with 70%, you can imagine maybe you're going to get a scalable lattice out of this. Then there's the question of the coherence time. You want to improve that with donors, but nitrogen is not the good donor because it gives you spin impurities, it gives you charges. Turns out sulfur gives you just as good charge stabilization, but it doesn't affect the coherence time of the NV. And so sulfur is a good one. Okay. The question is, how small can we make the nanodiamonds eventually and still have stable NVs? Well, that has to do with how close the NV can get to the surface and still be an NV. So to do that, we did an experiment with nitrogen-rich diamond. We made ultra-shallow NVs, just a couple of nanometers, and we find that with these ultra-shallow NVs, we get beautiful ODMR contrast. We verify they're shallow because we have a region where there's a fret absorber and a bare region, and we can see that we're absorbing most of the material. So that means we're considerably less than 5 nanometers. And if you look at even the optical spectrum, you see differences. You get these little dips in the optical spectrum, as if the phonon sideband has narrowed at the surface. And so we can get really close to the surface. So now how are we going to scale this up? How are we going to make a lot of these? Turns out that if you're making nanodiamonds, the sp3 is the most stable form of carbon up until around 10 or so nanometers. Okay, so you don't need high pressure to grow nanodiamonds, but you do need to pay attention to the surface. You have to have the hydrogen termination. And so with that in mind, we decided to try to grow at lower pressures. This is one of our first growth. We get reflux growth in DMSO. Okay, and we surprisingly got some diamonds under these techniques. The yields weren't high, so we had to try a couple other techniques. But eventually, we essentially put everything into an autoclave so we could get higher pressure. We added some methylating ingredients to try to improve our yield, and we got many more diamonds. And then we implanted these with silicon. Okay, so we did silicon implantation, and we got a few fluorescent spots. Okay, in each spot we have a complex spectrum which contains the NV spectrum. It also has a silicon vacancy, which shows up much more if you do red laser excitation. And you see the NV0 contribution is very small. So these have high charge stability. And in fact, we see this charge stability in the crystal that has a lot of nitrogen. But this doesn't have a lot of nitrogen. And we can look at the ODMR, and we can see there's not any splitting. So the nitrogen content is very low. And also the creation content of nitrogen vacancies is very high because we have the same ratio of silicon vacancy at the NV in each spot. Okay, what that means, if we say we assume we have one nitrogen in each crystal, we implant the silicon, well, that means that nitrogen that was there had a very high probability of converting to NV. So the only way to explain both of these, the charge stability and the high conversion rate, is if there is sulfur in these nanocrystals. Okay, but our growth material is sulfur rich. And so it's not unexpected to be able to get a part per million of sulfur content. So we think this is going on. We're going to do more experiments to test it. In the meantime, we have to improve the yield. Remember I told you that we didn't have enough material. We had enough to test it and see interesting things, but we didn't have enough to give anybody. So now we've experimented with some hydrothermal growth, growing from naphthalene derivatives. And if you do that, again, it's not a very high temperature, just barely above atmospheric pressure, we can get a lot more diamonds. And you can see that they're nice and round. The average size is 5 nanometers, not a huge distribution. They have all the right characteristics. They have the right patterns. So we're basically in the process now. We found a couple of NVs in these. We weren't able to irradiate yet, but we did find a couple of nitrogen vacancies in these. And basically, I don't have the data here, but essentially they have T1s on the order of half a millisecond, which is very, very good for a nanodiamond. And they have very large contrast in their optically detected magnetic resonance. So these are very high quality diamonds, and they're very small. Okay, so since it looks like we're getting close to being able to do something like this, how would we use this? Okay, so if we can make entanglement, if we can get two very close together, okay, and we can make entanglement, how can we use this? And so one thing I want to do is make a magnetic gradiometer.
Sorry to interrupt, but you've used up 20 minutes already. So if you could finish really quickly, it'd be good.
All right. So a gradiometer is better than a magnetometer if you're going to measure small things, because the gradient is large as the source of the field is smaller. And so you can do either incoherent subtraction, basically measure magnetic fields at 2 points, incoherent, or you can do coherent, and you do that, and you need entanglement to get that. That will give you better performance. Okay, so basically, this is what we're trying to do. We're trying to grow nitrogen pairs in seeds. We're trying to add carbon-13 for a storage register. We're trying some alternatives by implanting nanodiamonds, and we're trying to create ST1s. Okay, so in summary, I told you how we're making higher quality nanodiamonds. We're looking into better color centers than the NV, and we're starting to think about algorithms for entanglement for improving the sensitivity. And this is just a paper that describes some of the low pressure growth that's going on. Okay, so that's it.
Okay, thank you very much. That's remarkable work. I know how difficult it can be to make materials work for you. Do you have any questions from anyone? Okay. Well, thank you very much for an interesting talk. And let's move on to our last talk. This is a contributed talk, I think, given by Ilya Fedotov from the Moscow State University. And the title is Ultrasensitive All-Optical Thermometry with Germanium Vacancy Centers in Diamond and its Heat Penalty Function. So please go ahead.
Sorry.
We could just see your screen a moment ago. It was fine.
And is it fine right now?
Yep.
Okay. Thank you very much. I'm really glad for this invitation. I'll try to be in time, and my talk here is about unpublished work with a much larger number of co-authors, which I'm not able to publish by many reasons. And it is about ultra-sensitive optical thermometry with germanium vacancy centers in diamonds and its heat penalty function. So, as we have all heard a large interesting talk about nitrogen vacancies and other color centers, I would like to talk about some of its application. And I will go back to biology, where temperature is a really important physical value that controls almost all biochemical processes. And even more important, it becomes when we are trying to use temperature to control neurons, to control some function of brain. And how does it work? So in nature, some animals are sensitive to temperature. Rattlesnake is a good example who uses thermal temperature thermal sensitive channels to detect heat from mice. This study is lasting for years now, and it starts from investigation of physical principles of how does this channel work, and went to the problem where one should control temperature at a cellular level. To measure at that small level with high accuracy, diamond looks like color centers in diamond looks like a good candidate to fit this problem. And there are a lot of work that show that you can apply diamonds to biosensing, thermal biosensing, and the question which rarely comes is what is the limit? How sensitive could they be? And here we can see a number of color centers in diamonds, like nitrogen vacancy centers and germanium or silicon vacancy centers, which are different in symmetry, and they have a different relation of energy inside zero phonon line and phonon side band. So to measure temperature, you can use any physical value starting from splitting of spin sublevels and ending with estimating of zero phonon line position or the Debye-Waller factor, just measuring spectral an optical range. But the problem is that when you measure temperature, you have to use optical pump, no matter what method do you use. And here you come to the fact that all those diamonds can have some level of quantum efficiency, which is very low with silicon vacancies or germanium vacancies with different estimations from 5 to 20%. And all other pump power goes to heat your sensor. In nitrogen vacancy center, quantum efficiency is much higher, closer to unity, but large zero phonon line gives you a problem that the difference between your pump and fluorescent spectrum again goes hitting your sample. So a real measurement usually is a trade-off between sensitivity and heat penalty. And a funny fact that if you will take all numbers like line width, slope of derivatives, and take into account different quantum yields, you will see that temperature sensitivity of different color centers is more or less on the same level. It could be like 2 or 3 times better or worse, but more or less in the same order of magnitude. Take into account that heat penalty. So to show that it is really useful, I will probably skip a few slides due to lack of time. So here you can see thermal measurements of single cells with all optical heating, where you can control the thermal distribution with really high precision in time and space. It is optical temperature measurement in mice in vivo, where you can also use diamonds with some really interesting features which comes from measurement spectrum through a waveguide, which is bending by mice. Going back to this talk, I would ask, can we go to the limit of sensitivity? What should we do? So we have made a simple experimental setup, which is tuned precisely to collect all photons, as much photons as possible from a small few micron diamond. And we had used approximation of with germanium vacancy centers, and we have used simple approximation of its spectrum and tested different parts of the spectrum or some linear combination to go to the limit of temperature sensitivity. And what is usually expected that your thermal sensitivity is proportional to the square root of pump power and time of integration. So what we get here, so first here you can see calibration of the Biwaller factor, line width, line position, as a function of temperature. And again, some linear, you can calibrate linear combination as a function of the same, as a temperature again, using power dependence of all these values. So here you can see sensitivity, which is achieved by them. So by solid lines, you can see dependence, which goes as a square root of number of photons. And here you can see real experimental values by dots, which is flattened out, and so which is proportional at low pump power and flattened here at high pump. So what is going on is that diamond is hidden by its nature. And it is, as I told you before, it's not a problem of certain experiment. So here, some part of heating, again, is a feature of sample. But heating is more or less a fundamental thing as a result of measurement. So as temperature of diamond is growing, all other parts of the spectrum are flattened. So you have worse the bipolar factor, you have wider line width, and as a result, you go to the limit of sensitivity as a result of heating, not as a trade-off. And here we can see that we've got something like 1.5 millikelvin per square root of hertz at average heating like kelvins. And our best results we could get at much higher pump power and with high heating of diamond is sub millikelvin level of sensitivity. Thank you for your attention.
Okay, thank you very much. We have time for some questions. If did I understand correctly that it's absorption of the laser light that's causing the material to heat, and so
yes. So
okay.
To measure something, light should be absorbed.
Right.
And that's why the heating is always going with measurement.
Oh, I see. Okay. Yeah. Anyone else have a question?
Just a quick question.
Yeah.
Do I understand correctly? This heating also sets the limit to what you can do and how fast.
Yes, sure. And it is even more important in biosensing when you're never able to work at high sensitivity, which you write in articles.
Mm-hmm.
So you should keep your overheating like on the level of 1 Kelvin at most.
Mm-hmm. Yeah.
Okay, I don't see any other questions. In which case, I'd like to thank all the speakers for a series of very interesting talks, and I'll call the session to a close.
Thank you so much, Philip.
Yeah. No problem.
You did a great job keeping everyone clear.
Well, they were all very well behaved, so that's good.
Just a reminder, these talks will be available in a recorded form. I know that it's hard to compete with Olga's seminar in real time, but we'll have more audience through these laser physics Zoom links and on YouTube for your recorded talks. And we'll continue in 15 minutes. Phil Hammer will chair the next session. Vlad Shalayev will be the first speaker. So we'll take a short break and continue. And then, of course, tomorrow we'll all be there for Philip's plenary talk, and then more talks of our seminar.
Okay, well, bye. See you
Bye.
again.
Bye.
Bye.
Thank
Bye.
you.
Thank you.
How are you, Phil?
Okay. Not too late here yet.
Where are you in Germany? Oh, okay. And how much longer?
About another week.
Okay. Okay, enjoy it. I'll take a short break and come back here.
Okay. Yeah, I may take a break too.
12 or 13 minutes. Yeah. And then Vlad, yeah, I'm sure Vlad is ready. So, and I see everyone else. Okay. Bye.
Bye.
See you soon.